Hey, and welcome to SanfordFlipMath. We are working in PreCalculus, and we are working from the book by Demana, Foley, Kennedy called PreCalculus, Functions and Graphs, 4th or 5th edition. And we are deep in the throes of Chapter 3, which is about exponential functions and things that relate to that. So this section is actually about log functions, logarithmic functions, and just the operation of doing a log. So most of you have seen this before, but I'm going to kind of pretend like you haven't, although I won't spend my life on this, just setting up what it means. A logarithm is a way to rearrange an exponential expression. Like so, for instance, let's say we have 2 to the third equals 8. And if for some reason we need to solve for that exponent, now in this case we already know the exponent's 3, but sometimes we need to solve for that exponent, so maybe there's an x there or something like that, we'll see that in a minute, then we need a way to rearrange this and solve to get that by itself. And a logarithm is that. So you start out with log, that's short for logarithm, and then you put the base in the bottom, and then whatever the answer from that exponent was goes in. That's what the operator is operating on. That is the argument of the log function. And then it's equal to whatever the exponent is. Okay, so just to kind of do a little color coordination here. So, all right, and that's probably enough. Okay, so you're going to hear me say this a lot, but I need you to notice that this whole log expression is equal to the exponent. Okay, so that's what a log is basically a log is an exponent. A logarithm is an exponent. The answer to the log is the exponent. That'll help you remember where to put things. The base goes in the bottom, the thing that was raised to a power, and then the exponent's on the other side, and the only other place is that little guy, and that's where the answer. So again, the idea here is 2 to the third equals 8. Okay, and I know that feels weird to write it in that order, that arrangement, but that is how the log works. Okay, so let's say we had something like 2 to the x equals 4, and so what I want to know is what is x. Well, if I was going to write this in a log format, log base 2 of 4 equals x. Again, that exponent is over there on the, so here's that exponent, here's that exponent. The exponent's over there by itself. The base is 2, here's that 2. Okay, so this is exponential form. This is logarithmic form. Okay, and if you're going to read this out loud, this log form, like this one for instance, when you say this base, you have to say the word base. Isn't that clever? Okay, so this is not log of 2 of 4. This is log base 2 of 4. Or you could say log of 4 base 2. Either of those are fine, but when you're talking about the 2 in this particular example, you have to say the word base. Okay. All right. So let's do some more examples with this, and I have the rules, so for what we're doing so far over here, and we're just a reminder that those two go together. Okay. So we're just going to do some basic calculation kind of stuff. So like log base 5 of 5. Okay, so that's how the problem might look at this point. And really the question is, and if you have a hard time picturing this, I'm going to add in a little x here. I'm going to put an x there. And so here's the base to the exponent power equals whatever that was. And I know that's harder to track because they're both 5s, sorry. And so since these bases match, the exponents have to be equal to each other. Well, I don't see an exponent for this 5, so you're just going to kind of stick it in there and say, oh, it's 1. So in other words, x equals 1. So the answer to log base 5 of 5 is 1. Okay. I would highly recommend, until you get like super comfortable with this, writing out this exponential form. Rewrite it in exponential form first, and then make the exponents equal to each other. Okay, so for instance, let's do log base 3 of 81. Okay, so again, the thought process here is that I'm going to make that equal to some number. Okay, and then 3 to that number has to equal 81. Again, the idea here is, and you're going to hear me say this a lot, the log is the exponent, so it's got to go up there. So 3 to what power is 81? Well, at this point, you can just kind of do a little guess and check thing. I know 3 to the 1 is 3, sorry. 3 squared is 9. 3 to the third, that would be 27. 3 to the fourth, that's 81. Oh, that's it. Okay, so remember that the goal here was to say what the exponent was. So 3 to the x equals 3 to the fourth. So I guess that x must be equal to 4. Okay, so log base 3 of 81 is 4. Okay. Okay, let's do a couple more of those that are a little more, I like to say interesting, but I know most other people are going to say hard. Okay, let's do log base 4 of 8. Okay, now again, it probably won't say equals x on there, and so you're basically just supposed to be evaluating log base 4 of 8. Well, the problem that I have with this is, I know 4 times 2 is 8. Okay, sorry, let me back up. I'm looking for an exponent that when I raise 4 to that power, I get 8. All right, so back to where I started to go. 4 to the 1 is 4. 4 to the second is 16. It's got to be somewhere in between there. I mean, that's a bit of a problem. Okay, so what I'm going to do is actually, I know that 4 is also a power of 2. So I'm going to write this as 2 squared to the x. And then 8, well, 8 happens to be a power of 2 also. 2 to the 1 is 2, 2 to the 2 is 4, 2 to the third is, there it is. So this is 2 to the third. Well, I can simplify this exponent on the left side a little bit and call this 2 to the 2x. So that should be equal to 2 to the third. Now my bases match. Okay, so this base now matches this base. Sweet. So if that's true, then my exponents must be equal. So 2x equals 3. X is 3 over 2, or if you would rather write 1.5, that's fine. And I think you need to notice that 1.5 is certainly between 1 and 2. Okay, so there it is. That is log base 4 of 8 is 1.5. And if you type into your calculator, 4 to the 1.5 power, base to the 1.5 power, it'll actually give you 8. Okay, one more of those. Let's do log base 9 of 1 over 27. Ooh, that looks like a lot of fun, doesn't it? Okay, maybe not. Okay, so again, I'm going to make it equal to x, and I'm going to rewrite this in exponential form. So the base to the x power equals 1 over 27. Okay. Now, the process I'm using to make this work is rewrite this in terms of the same base. Well, I know that 9 is 3 squared. So 3 squared to the x, because it said 9 to the x, well, 3 squared is 9. The trickier part right here is this guy. Well, I think we've seen this morning, or today, or whenever you're watching this, tonight, that 3 to the third is 27. I think that came up earlier. But the problem is how do I get that to the denominator? And I need to remind you that if I have something raised to a negative power, it is the reciprocal. So in other words, this is really 3 to the negative third. Okay, so 3 to the third is 27, so 3 to the negative third must be the reciprocal of 27. Okay. All right, so this is where I'm working right now. Just like I did on the last one, I'm going to do 3 to the 2x equals 3 to the negative third. So solving this, I know that the exponents have to match now, and I can divide both sides by 2. So x equals -3/2. Okay, so now, just so you see what happened here, my answer is -3/2 or -1.5 if you'd prefer. Now, I need you to be able to understand why that works. Okay, so we're saying 9 was the base. The exponent we're saying is -3/2, and supposedly that's equal to 1/27. Okay, I want to show that that actually is true. Okay, remember that a denominator for an exponent means the root. So in other words, this means the square root of 9. Then the numerator of that is the power. And then what I'm supposed to do is -1 power, so reciprocal. So now I know this, none of you are going to write this on your own, I would think, but I need you to be able to think through this logic. Okay, so if I do the square root of 9, that's 3. I'm going to cube it, that's 27. And if I do the reciprocal, that's it. So my point is that checks out. Okay, just don't get lost in this, but the answer was this, -3/2, or if you prefer, -1.5. Okay. Okay, let's do a couple that are backwards. Okay, so the idea being, let's say I have log base 3 of x equals 4, and I want to solve this for x. Well, how do you get rid of a log? Well, if you're trying to get rid of a log, you go from log form back to exponential form. Okay, so the base is 3, the exponent is 4, equals x, and I think we just saw a minute ago that that's 81. That's it. Now this can get slightly more interesting. Let's say I had log base 3 of x minus 2 equals 4. Ooh, that's much harder. Okay, maybe not. Okay, so base to the exponent equals x minus 2. Okay, so this is 81. Sorry, had 81 on the brain. X minus 2. So add 2 to both sides. Okay, and again, just to do a quick confirmation here, 83 minus 2 is 81. 3 to the 4th power is 81. So that works. All right. Need to take you on a little trip. What if I want to graph y equals log base 2 of x? Okay, so we're going to graph this. We're going to do domain, range, vertical asymptotes, horizontal asymptotes. I already said graph. Anything else that might come up. Okay. Well, the problem is that as I put in, I'm going to do a table of values because that's what we do when we don't know what to do. As I put in x values, let's say I put in like -2, -1, 0, 1, 2. Okay, now don't get too far ahead of me because I'm going to redo this table in a second. Okay, so don't write that down. I just want you to listen. If I try to put in -2 here, and I'm doing log base 2 of -2, 2 to what power is -2? Not a negative power, because negative powers make fractions. Remember that the goal is to find the exponent. I want to know 2 to some power equals, whatever, and then the question is, what's that exponent? Well, this is actually kind of hard to do unless you're like really smoking good at logs. So I'm going to make a recommendation that we switch this. I'm going to rewrite this exact thing in exponential form. Okay, so the base is 2. The exponent, remember, is the answer for the y, and then that's equal to x. And it's actually easier to calculate this if I put in y values instead of x values. Okay, so let me back up, as promised. I'm going to put in y values this time. And I'm going to put in the same kind of numbers I would have put in, but I'm going to put them in for y instead of x. I'm really putting them into here because this is equivalent to this. These are the same thing. Okay. So 2 to the -2 power is 1 over 2 squared, so 1 over 4. And that's actually my x value. Okay, I know this feels weird, just kind of bear with it. So 2 to the negative 1 power is 1 over 2. 2 to the 0 power is 1. 2 to the 1 power and 2 to the second power. Okay, those are easy schmeezy. Okay, I'm going to take this off so I can have some room here to work. Okay, and let's just do a little graphing. Guess I don't really need all that space, do I? Okay, so here we go. 1/4. So if this is if this guy was 1, then that's a half. So 1/4 negative 2. So somewhere over here. 1/2 negative 1. 1 0. 2 1. And 4 2. And if you keep this going, it's going to look like that. And now down here, it's going to keep going down forever. Okay, a couple of things. Your calculator can't do that. It runs out of x values getting closer and closer to 0. It can't keep this going forever. You need to know that this thing goes down forever. Never crosses the axis. In fact, it approaches it and it gets closer and closer and closer and closer. Sorry, that's supposed to be crosses, a C. Okay? So the y-axis, also known as x equals 0, is a vertical asymptote. There are no horizontal asymptotes. I guess I'll just say none. Okay. The domain then is the stuff to the right of 0. The range is all real numbers. Now, what I would like to do is take just a minute to do a little bit of a contrast here. We've been working with something that looks kind of like this for the last few days. Okay, so let me draw your attention to this. We've been working with, instead of 2 to the y equals x, we've been working with y equals 2 to the x. Okay, so what we had up here, again, was 2 to the y equals x. Okay, so that was 2 to the y equals x. And this is y equals 2 to the x. Well, what do we call that when we switch x and y? Whoop, that was funny. I did not expect that. Must have hit the button by mistake. So 2 to the x is, and x equals 2 to the y are inverses. And remember, this is really the same thing as y equals log base 2 of x. Okay, here's the point. This guy and this guy are inverses. So think about what we've been saying about y equals 2 to the x. So this equation has a domain of all real numbers. The range is greater than 0. It has a horizontal asymptote of y equals 0. Its graph looks like this. If I then go to, okay, so I think we were talking something about inverses, so let me go back to this then. We just went through this, and I just want it in the same spot here. But we just did a quick little graph of this. This is y. I don't need to write that again. This is y equals log base 2 of x. Okay, and then so for this one, the domain is y greater than 0. The range, all real numbers, and instead of a horizontal asymptote, it's a vertical asymptote, so it's x equals 0. Okay, so notice that all of the x and y stuff switched. What used to be horizontal is now vertical, and that y changed to an x. Okay, here's that reflection over the line y equals x. The graph looks like that. So I just need you to see that connection that logarithms and exponentials are inverses of each other. All right, I just have 2 quick little ideas to chuck in here so I can finish out this list that I have here, and that is sometimes you'll see stuff like log of 100, and what you need to note is I don't see a base written there. If there's no base written there, this is called a common log or a common logarithm, and it is assumed it is base 10. Now, base 10, because our numbering system is base 10, and it comes up a lot, and it gets used in scientific notation quite a bit. So if this is 100, then again, this is implied that that's 10. So 10 to what power is 100? And that would be 2. Okay, so again, if we were going to do the log of 50, again, if there's no base written, this is assumed to be base 10. Now here's the problem is 10 to what power is 50? There's no way to write 10 to some power and get 50. And you can't just do, well, 10 to the second was 100, 100's half, so half of it. No, you can't do that. You can't and do anything like that. But on your calculator is a clever little LOG button. So you can actually type LOG. Notice there's no base there. LOG of 50, and it's going to tell you whatever the log of 50 is. Okay, now I know that it should be somewhere between 1 and 2. Okay, so like if we just type it in, okay, I'm actually typing, you can't see me typing, 1.698. Okay? Okay, same idea. You're going to see written down things like this. Now this, if you see ln written there, it automatically means log base e. So this is log base e of 3. So log base e of 3. So remember that e is that number that's like 2.718-ish. It comes up in exponential things actually quite a bit. This is called the natural log, and it probably came from French. There were a lot of French folks working on logarithms and exponential kinds of stuff. Euler being one of them, and I believe he was French. That could be wrong, but I think that's correct. So is ln probably like log natural or something like that. So this is natural log, and again on your calculator. Now why they decided to type it in with capital letters, that I don't know, but when it shows up on the screen, it actually shows up lowercase. And so you can just type in ln of 3 equals 1.0986, whatever. Okay, or if you saw something like the natural log of e to the 5th, well, what power is e being raised to? Remember, this means log base e of e to the 5th. Well, that should be kind of obvious that it's 5. It's saying what's the exponent for that base. All right, we're going to leave it at that. We have talked a little bit about logs here, and we will do more practice and more discussion in class. Thanks for watching. Bye.